So go ahead. Look, so far I've described just particles, but particles have properties. So I can be interested in identifying properties of the particles and to describe mathematically the properties of the particles. So I'm interested not only to see how these particles move, which is motion, but I want to describe how the properties of the particles evolve, change during the motion. And then I need also some mathematical framework to do that. And in fact, we have two different mathematical frameworks. One is what we call the Lagrangian description or the material description. I prefer the word material. And the other one is the spatial description. What is the difference between them? Well, it's a conceptual description. The material description is a way of describing mathematically the properties of the particles, or the properties of the continuum medium, but defining them in terms of the particles. So essentially, if I'm looking, for instance, for density, imagine that I'm just moving that, and every particle changes the density because I'm compressing and whatever. Okay? So I want to describe the density of every particle. I could say, well, at this time, at this reference time, the particle 1 has density 1.5. The particle 300,000 have a density 2.5. So this describing the properties in terms, along time, in terms of particles labels, in terms of particles names. So in other words, it's like, look, you will use that term. It's like we were writing the particle. We follow a given particle because I am just identifying the property in terms of the particle. And at every time during the motion, I identify what is the value of the property I am interested in. It's like if I had a densimeter, an apparatus which is able to measure densities, and then I continually, I'm following the particle, and keeping the attention in that particle I'm writing in, I just identify what is the density at every time. That's one possibility. The other possibility is what is called the spatial description. In that case, we are not driving a particle, we are staying in a certain spatial point. And in that sense, I'm measuring what is the density of every particle that passes at every time through that spatial point. So I can say at this spatial point, 1, 2, 3, at time 1, the density of the particle that is at that time 1 at this spatial point is 1.3. But at time 2, the density of this particle would be different because it would be in another point. But now I'm just describing what is the density at this spatial point. So somehow the image that can be given is that in the spatial description of a properties, I'm doing pictures of the whole space, and in these pictures I see at a given spatial point the value of the properties at a given time, at the time that I take the picture, then at that time I see the properties. If I was able to see densities in terms of colors, for instance, I would see the density at every spatial point at this time. At another time, I would take another picture. Okay? So now I would say for every spatial point, the density of that particle, those particles that are staying, that are occupying that position at this new time. Okay? So that's the spatial description. The material description is completely different. I'm following particles. I'm writing one particle and I'm giving the evolution of the density of the property of this particle along time. Then I write another particle and I do the same and so on. So why these are two possibilities that now can be just expressed in terms of mathematics? Why I'm doing that? That's for comfortability. So, I mean, we can see that we can pass from one description of the particle to the other, right forward to, by using the equation of motion. The advantage is that they are more convenient in certain contexts. For instance, in general, when we study solids, they don't change the configuration too much along the motion. So, if I'm studying this table, and I just put my weight on the table, in fact, there is a motion of the solid. Very small motion of the particles, because there is some deformation, you know already this concept. So, but the reference configuration and all the present configurations I'm interested in are very close to each other. Even if I consider large deformations, we go that. Even if I do that, then, I mean, the original configuration is that, the final configuration is that, they are relatively close to each other. But now, imagine that this is a fluid. A river, for instance. And now I consider a set of particles of the river when it's in the mountains. These particles, the set of particles that constitute the continuum medium, certain number of particles of the river, when they arrive to the sea, the configuration is very different of the one that I had at the beginning. So in fluid mechanics, in very deformable continuum medium, it's more comfortable to use the spatial description. Whether in solid mechanics, it's more comfortable to use the material description. They use also the names Lagrangian and Eulerian, because Lagrange, the famous scientist, an engineer by the way, was the first one that identified that way of describing the properties of a continuum medium, and Euler, a famous mathematician that you already know. Euler is famous by many things. So identify that. So in some books you find Lagrangian and Eulerian, but it's more descriptive to talk about material and spatial configurations. Well, I already commented that. That is the image that in the spatial descriptions I just follow a certain particle which is occupying different positions along time, and I'm giving the evolution of the property for these same material coordinates. Along time. Whereas in spatial already description, I just pay attention to a given space point, and then I just say what is the property at this point, at this specific spatial point, of the different particles that reach that point at different times. Okay, that's the concept. Well,